Good afternoon, everyone. I'm really excited to be here, my first time in Tel Aviv. So I'm Rakesh Cheerla, I'm a product manager. I work with Xilinx customers, and then I work with my engineering team. So I'm trying to get a perspective that is somewhat customer-focused. Our customers are all developers, and then somewhat more hardware, software kind of things. So our journey in the data center has begun about 5 years back or so. We have been working on software developer platforms for the last 5 years. Essentially, these are some of the areas that we have worked a lot on. Analytics, video transcoding, machine learning, and so on. And the initial foray was more into the compute-focused workloads. So we have focused a lot on compute. And then a couple of years back, we launched the Amazon Web Services, FPG as a service instance. Amazon launched that, actually. And then we followed that up with a few additional cloud offerings with Ali Cloud and Huawei and so on, right? So essentially, the company has been focused on transforming into a software developer platform company. And the focus has been primarily on the compute side of the house. So compute offload has been the main way of looking at this. The last 2 years, what we have done is we have seen that the network and the storage tend to be great areas to work on and improve. So that's how the computational storage team came about 2 years back. We've been working very actively in this area, and then I will be covering part of what we have been doing and what some of our customers are doing today. So I think I have 35 minutes today. You'll be bored if I talk for 35 minutes, so please ask questions. I'll be happy to answer questions as I go through the presentation. We'll cover more of the storage side of the house today, mostly computational SSDs, but also a little bit of computational storage, concepts around that. So I want to start with some of the data center trends and some of the enterprise trends and tie that to computational storage. Why do we think the time is right for computational storage? This is not a new concept. There have been quite a few attempts at this, so we want to make sure we understand what's going on in the ecosystem. So I'll dive deep into some of that, and then talk about why it's so important to move computed data. And then finally, quite a bit of information on the work that we're currently doing at Xilinx with some of our customers. Okay? Any questions so far? So the first chart here is actually showing the global internet traffic. As you can imagine, a lot of traffic driven by video. Netflix and YouTube are the top two workloads. And very heavy video processing going on in the internet. So this is kind of a huge trend. And the mobile trend with iPhones and Amazon with the transactions, retail, and Google search, right? These are all like trends that are driving a consumer revolution. What that does is you'd have millions of kind of users at the same time. Very microservices because there's like tons of parallelism in this kind of workload. So that's where the world is going. I wanted to quickly touch upon Facebook. I think the previous speaker also touched upon that a bit. Facebook has about 2 billion users, and no two users' pages are the same. Each one is unique, and each one feeds to maybe hundreds of connections in a very rich graph, and it's getting updated constantly real time. And I think if you think a little bit about it deeper, right, that's actually very complex, very kind of intricate in structure. So I think that's what we are getting into now is like the infrastructure needs us of such scale and such kind of rich diversity that we need some of the newer paradigms like computational storage to kick in. So in terms of, I think the speaker earlier on, I think Yusuf in the other room earlier on had talked about the data being cold, which is very true because we are not able to process the data today. We are in a, so what's happening is that we have a lot more data processing frameworks now. So I think analytics is going to be big in this era. I think the next 10 years are about being able to bring the data's temperature up. You want to do more analytics, you want to do more machine learning. And I think a lot of those frameworks end up being very varied depending on the various data sources. So what that does is you need a system of like workload optimization. So the last 10 years have been primarily about software optimization, new software frameworks. I think the next 10 years is about the hardware optimization too, because you need to be able to process them at a cost that makes sense. At the scale that things are happening, the cost needs to go down. And that's where I think, for example, on the AI side, you see tons of startups doing hardware. And I think you're going to get to a stage where you'll see a lot more hardware needs in terms of in terms of all kinds of data processing units that are required, and some of those will fit into the computational storage paradigm. So that's kind of the thesis here. And then if you look at the infrastructure of the major cloud providers, Amazon Web Service, Microsoft Azure, and Google Cloud Platform, these are the top three. There's not too much information on what's inside these kind of internal clouds, how they build their internal infrastructure. There's some information, but I think what you can infer easily is that these are of exponential scale. Cost is of primary importance, because if you cannot lower the cost, you cannot scale at the rate that you need to. So exponential scale, very massively parallel. We talked about Facebook. You could see Uber riders, for example, you have millions of riders, and they're all interacting with the system on real-time basis. So very real-time, massively parallel on Uber. And if you're doing Google Maps, which is the #1 workload on the mobile phone, that's all interactive, right? So you're seeing interactive, real-time, massively parallel happen so often that I think you need to start thinking about this in terms of the consumer revolution that's happened and how the data services are going to interact. I think there is a huge opportunity to innovate. I think that's why I think the next generation will need a level of hardware innovation too. And then again, like there is huge data sets. Data is growing exponentially. And we talk a lot about unstructured data, which is true. Most of the data that's coming in is unstructured. That said, you need to lay upon some structure upon it, some level of structure to be able to analyze it. So I think structured and unstructured mechanisms to analyze data is going to be critical. And since the economy is actually very data-driven now, data is called the new oil. For a reason, if you're looking at machine learning, for example, what we say is that the algorithm itself is not that important. The amount of data you get is even more important than the algorithm itself. So what is happening is the world is getting a little more data-centric. The data has gravity now, and that gravity will pull the CPUs towards the data. And that's really what we are arguing here in terms of the different trends happening in the data center. Finally, this is a slide from Google. Essentially, this is analysis of like an SSD drive today. SSD drives are extremely parallel. You can drive something like 100 gigabits per second network across a single SSD drive. What that means is that in a single building, you would need a 5 petabytes per second network, which is the bandwidth of the entire internet today. So the network is a fundamental bottleneck. Even if you oversubscribe this 10 to 1, you still have a 500 terabits per second network within your building. So I think going forward, our fundamental bottleneck is the network. And what is the best way to solve the network bottleneck? That approach is to reduce the amount of data going across the network. And I think that's where you see that the computational SSDs become a critical component of the next generation infrastructure. Because what you can do is you can do a ton of processing within the SSD and reduce the pipe of data going back across the network. And that, I think, is going to be required for the next generation infrastructure. So essentially, in terms of the trends, I'm trying to tie these trends to two things. One is there's a lot of variety of workloads that you can optimize hardware for. And then the second one is that storage is going to be, computational storage is going to be an important aspect of reducing the network bandwidth. And I think that's the fundamental bottleneck in the system. So network bandwidth reduction through computational storage is going to be an important component of the next generation infrastructure. So any questions for me so far? OK, let's move on. So anyone here from the Annapurna team here? AWS Annapurna team? Not really. So I'm a huge fan of the Annapurna systems. Essentially, there are 4 chips here. And the part that I get really interested about is the system controller, the Nitro control chip. What that has done is it has decomposed the server into its constituent parts. The Nitro controller chip now can control each part of the system. It can control all the different components here, as well as the CPUs here. So what's that done is now you have a mechanism where like the system is not tied to the old like BIOS systems and such that would actually updating the firmware and such that would actually limit the amount of innovation in the system. This system is innovative for one reason. In 2017, the system got introduced with the Intel CPUs. And in 2018, it got introduced with the AWS Graviton, the ARM-based systems. I think Neil's going to be happy about that, right? So the Graviton system. And it has the same system components. The Nitro controller is what controls the process. What this has done is something fairly, I think, fundamental. If you go back to first principles, what this is doing is it's basically making the CPU another workload optimized processor. Essentially, it works just like the same as a GPU or a TPU or a FPGA-based accelerator. The CPU is now the same thing in this particular system. And beyond that, this is one example. Many of the hyperscalers are following a similar route. And then I'd also say that the enterprise can't lag behind too much, right? They're going to be competing with the cloud in terms of market share and mind share. So I think this is kind of more of an ecosystem view of what's happening that is kind of really allowing innovation in the ecosystem. And I think this is what will allow us to get to the next generation of infrastructure. So I kind of see this as an important business reason for what's happening in the infrastructure. So if I'm looking at the next generation of infrastructure, my view is that you'll have heterogeneous workload process. And what do I mean by heterogeneous workload process, right? That could be a CPU. A CPU is a very good general purpose engine. So that could be a standard CPU. And that could be a CPU from ARM or from x86, Intel, AMD, and such. So that could well be a CPU. But it also be a GPU. It'll be a tensor processing unit. It would be a FPGA-based video acceleration engine, for example. Video is a huge workload now. So the way I look at the heterogeneous workload processor is that it's basically processing a workload. And it is very specific because the workloads have become pretty specific. So that's kind of the workload processor there. And then some controller outside of the workload processor is going to control this system. And essentially, you'd have racks of this, and you would have computational storage within the rack. And also, in effect, actually, if you look at a lot of the all-flash arrays today, they're already computational storage arrays. Computational storage already exists today. And then more moving up is more the software, kind of the software-defined network and the secondary storage tiers. So the heterogeneous workload processor-based kind of approach gives you the flexibility to go process these workloads efficiently. So in a very timely manner, actually, the SNIA computational storage group was formed. The three startups here, Editacom, NGD Systems, and ScaleFlux, they were actually pursuing three different approaches. They all came together to build this kind of trailblaze on some of the concepts here. And apparently, all three understood that the market was big enough for all three of them. Not just that, they all three understood that the market was big enough to invite all the big guys. So this is kind of a huge thing where, like, last week was the first technical work group meeting, and we had a lot of discussion around how to standardize computational storage, all kinds of computational storage, not just SSDs, but how many of you are familiar with this SNIA computational storage group today? Have you? Okay, a few. So please take a look at it. This is certainly a very interesting effort where we want to take computational storage to be a very standard-based thing that can run on a standard server. And then be able to be discovered and then feature sets and define things like that. So it's like trying to standardize the software for this, the APIs, and making sure that we can actually, in a standard way, interact with computational storage. There is a few definitional things that's come up here. You could have a fixed purpose computational storage, which is more of fixed services. You'd have general purpose storage, meaning that it's kind of operating system capable. So could be ARM CPU, for example, running a Linux workload. So that kind of approach is what we would call a general purpose computational storage. So a lot of interesting work going on here. So if you get a chance, please take a look at SNIA computational storage and take a look at joining and participating in this really, really interesting effort. So wanted to talk a little bit about moving computer data. We'll start with kind of the standard approach, which was, like I said, the compute-focused path that Xilinx was approaching initially is that we have like a offload type of model where we put an FPGA card, a PCI card, as a computational storage offering, and there's an accelerator sitting on it. So what that does is, initially they started with OpenCL, but you could also do it with CC plus standard now. But the model here would be that you would actually copy data from the DDR into the accelerator's DDR, do a bunch of processing, and then write the data back to the DDR. And the storage path is actually separated out. That's the reason we call it offline. The good part is that you'll see that the CPU is actually showing green there. We offload the CPU, but there's additional copies to the DDR. So the DDR still tends to be heavily loaded, and the I/O tends to be heavily loaded. This is where we are doing a bunch of processing in the storage subsystem here. So imagine you're in the security line in the airport, and the screener is looking for your images, for example. In the current model, what you do, you'd move the entire data into the CPU. Could be 1 million people's images, right? They would all be moved to the CPU, and then you need to find, and that takes time. What this does is it'll basically do all of the processing within the SSDs, and then move the 10 images of me there into the CPU. And that's a much more efficient process, and that actually improves the time to insight. So you get much better application response time. So that's kind of the concept around computational SSDs. The initial applications we view are more in the analytics area, where you're processing terabytes of data. So a little more about moving data into storage. Now, in the traditional systems, you won't have the storage adapter, and these would be standard SSDs. In those systems, essentially, the network and the storage tend to cause interruptions to the application. The application is checking along, and then an interrupt comes through storage or network interfaces, and that tends to impact application response time. That's one issue. The other issue is that there's a lot of data movement going to the CPU. So there's a ton of data transfers going on. So putting a storage adapter or a computational SSD has a couple of huge benefits. One is that whenever there's data-intensive acceleration required, whenever there's data gravity, you can reduce the amount of data that goes to the CPU. So that improves the throughput of the application. And then as we reduce the interruption, especially if you add CPU cores there, what happens is you can move a lot of the software stack into the adapter itself or into the computational SSDs, and you can dedicate the CPU for application processing, so that it won't be interrupted as often. So it has very good latency benefits there. So looking at those two aspects, we kind of think that there's a place for both storage adapters and there's a place for computational SSDs in this framework. And the adaptive storage acceleration examples here have mostly come from conversations from our customers. So if you look at the top top four examples here are what we call storage services. These are more standard ones: encryption, compression, data dedupe, RAID and erasure codes. These have been there for a long time, particularly with all-flash arrays, right? What SNIA's technical work group is doing is it's trying to standardize this so that they can be discovered and deployed on standard servers. So that's the intent of the SNIA work group. And if you look at something like encryption, right? If you're doing encryption on the network, inline versus encryption on storage, data at rest is different. If you're looking at compression, video compression is different from image compression, is different from block compression versus file, right? So there's many flavors of these. So I have customers in different areas looking at these things. And the next set is really the database and the data-centric workloads, the key value offloads for object storage. Database, the transform of database, the ingest of database, and the query offloads for database are very popular. And the map-reduce framework is actually particularly suited to computational storage because you can map a software service, a portion of the software service that's data intensive, and put it in the ARM CPU or another CPU. I guess I'm using ARM a lot today. So, or another CPU, and put it in there, right? And that would actually, and sometimes it's just a container. NGD Systems, one of the startups for doing that, is just use a container and move it over, right? And what that does is it provides you great acceleration framework, right? And like we talked about, video has been huge. So video imaging, there's a lot of different IPs and startups that have worked on this particular ecosystem, providing the basic subsystems and the software to build video delivery, video processing, and video transcoding systems. And search is important, all kinds of search. And then machine learning, that's coming up a lot. So these are, I would say, the key workloads that I've seen from my customers. And there are actually, each one has many flavors depending on the kind of workload it's trying to optimize. So there's a lot of interesting work going on there. Any questions? I'll take a breather.
As far as I know, you have three different things on the FPGAs. One is pure FPGA, lookup tables, find data.
Yes.
But the other is still you have hard cores or ARM.
Yes.
And in the latest versions, latest things, you have the coarse-grained coarser-grained building blocks.
When you say coarser-grained building blocks, I'm not entirely sure what you're talking about.
The Xilinx
okay.
architecture has...
Okay, the math engine?
Yeah. Has large part that is not fine-grained information.
Yeah.
And the question is, this green block that you showed, FPGA, what mix of those, what's really needed as opposed to just having ARM or
So most of the accelerators are really dependent upon the fabric itself, which is the FPGA fabric. That's your traditional FPGA fabric, which you would program. So a lot of our newer hardware components are built upon C code using what we call high-level synthesis that's integrated into our tool flow. So what that does is you can build a hardware primitive from C code, and then that would be an accelerator, let's say a compression engine or an encryption engine. And then our platform allows you to connect that through an API, right? And then that API is used by, so essentially the FPGA fabric engine is a key portion, and that's connecting to the host itself. So a lot of the software is running on the host. But increasingly, we are enabling the ARM subsystem, which is part of our Zinc family of devices. What that does now is you can actually have a portion of the application now running in the ARM subsystem. And I think that's a very powerful capability, because now you can actually move chunks of software. And then what we do is you may run that software in the ARM, and it might run a little bit slower. But then you can actually use our synthesis tools to kind of look at the critical paths in the data path, and then offload that to the fabric, the FPGA fabric, right? And that'll give you the speed up. So that's the second piece of it. The third piece of it, the math engine, is mainly focused on machine learning workloads. So if you're looking at machine learning, or sometimes like DSP processing, some of the video might use it too. Those are useful there. So what we call as a software programmable engine is really based on the ARM CPU cores for Xilinx. And what we call the hardware programmable engine is the FPGA fabric. And then the math engine is really focused on machine learning inference primarily. Could be machine learning training, and could be a few other workloads. DSPs have been used for other things, including signal processing. It's basically a multiplayer accumulator DSP type with very rich fabric to connect it together. Okay?
I guess kind of following up with Tsaki's question, can you go back to a previous slide?
This one here?
Yeah. So, for example, in the right-hand diagram, what will be doing the IOs to the underlying storage? Would that be like NVMe hardware hosts, or would that be the ARM cores inside the FPGA? What do you typically see in that?
So typically in this model, I'll delve into that a little bit more in the later slides. But typically this is an NVMe system, and we use NVMe as a transport mechanism. And what computational storage is doing is actually it's defining some primitives. If you're doing compression or encryption, then you can discover those capabilities and run it. So it's running over NVMe. It's all NVMe or NVMe over fabrics as transport, one of the two mechanisms. And then you expose these capabilities. So that's the main mechanism of enabling these accelerators.
My question is that who is actually driving the actual I/O to the underlying storage? Would that be embedded CPUs, or would that be logic?
It would be a combination of both, right? So essentially, there's multiple paths here. In fact, you actually have a direct path from the CPU to the SSD itself. That path would be your standard NVMe endpoint. And then you actually have path between the accelerator and the SSD through a DMA engine. And then you have a path between the ARM cores and the accelerator. So there is multiple data paths here, which is what gives it the power. It is the ability to transfer data from, for example, the host into the accelerator's DRAM. That gives you the flexibility and power to do additional data processing.
I think the underlying question has to do with cost effectiveness, because FPGAs tend to be expensive, and SSDs are commodity, every cent counts. So putting in an expensive component needs to really justify itself and being extremely more effective. Otherwise, dollars to performance don't make sense. So I think this is really the thing we're trying to get a feel for.
So let me go into a little bit of high level of the cost equation itself. If you're looking at again, one of the things that's happened over the last few years is the drop in costs. But really, FPGAs are priced based on volumes. So at high volume, again, like these systems are being built today. If they're not cost effective, they wouldn't be built, right? So I think the perspective that an FPGA is expensive fundamentally is, I think, erroneous. So we can talk about this more if offline. I can't be talking too much about price and cost here on a technology conference, but I think it's a fallacious kind of thing.
Reconfigurability costs area.
It does. It does have some cost, right? It does have some cost, right? But if you're looking at an SSD drive, you're looking at a controller at NAND that may be $1,000 and a controller that may be $10. And fundamentally, if you add some additional costs may certainly being sub 100, right? You have $1,000 of NAND cost. So if you sub 100, then you're actually in the game. And one of the ways to look at computational storage has to be more in terms of the solution cost reduction. So let's say if you can use computational storage and be able to reduce 2 servers into a single server, right? Then you see the bigger advantage. But I'm saying it's still not a cost argument. I think the cost comparison with FPGAs is on a relative basis, right? It costs some money to reprogram the fabric. So I agree. But I'm saying the scale of device we have in our family means that the incremental cost is very small compared to the cost of NAND. So I think that's the fundamental part. NAND is going to cost you more. The controllers, even if they're FPGAs, cost you much less. So I think we can have that discussion a little further. OK. Please.
So regarding this picture of the three types remote, so I understand the middle and the left one. Regarding the right picture, so how do you handle the problem of if you want to do a logical operation on an application level object, it's not necessarily resides on a block SSD. So you don't have the entire context of doing this logical operation. So how do you handle this problem?
Yeah, I think that's a really good question, right? I think if you're handling block storage, then it certainly has certain limitations, right? You're handling block storage, and over time you can get richer kind of abstractions here. You can get metadata into the SSD, and I think it'll be a little while longer before you start getting file systems there. But I think that's the direction of where we should be going. And in fact, like you could have storage that's totally based on key value and not based on block, right? So those are kind of innovations that are in the works. And I agree with you. I think if it's mainly block based, then it certainly does limit you in the richness of the things that you could do. Okay? Let me proceed here, and we'll come back to questions. So what is a computational SSD, right? So I think fundamentally we see it as hardware accelerators there, which are reprogrammable hardware accelerators. And then we see CPU cores there, certainly. I think the CPU cores provide a very rich mechanism of taking current software and looking at what portions of that software are data intensive. What portions of the software require a lot of access to storage or memory, right? And then you can move that piece of software into the ARM CPU cores, and then you can start kind of interacting with the hardware accelerators, provide a very high bandwidth interface to the hardware accelerators to actually provide real acceleration. So the fundamental aspect of this kind of a design is that within a chip, you can have maybe 100 times higher bandwidth than you can have it across a PCI bus. And even if you're using multiple chips, let's say the controller is a different chip from the FPGA, even then you have a 3D package that has tons of bandwidth. So the interposer gives you terabytes of bandwidth, right? So we have an opportunity to build this kind of high-speed way that connects these accelerators together. That's one part. And then we also have the opportunity to optimize it, right? If you wanted to do some bulk moves for a specific workload, you could do that. If you wanted to do streaming interfaces, you do that. So it gives you an opportunity to optimize the system, optimize this computational SSD to provide really value to the application that you're trying to accelerate. So that's really the objective here. And then again, like a computational SSD is fundamentally a distributed scale-out component. So you can add an additional SSD, you'll be adding compute, you'll be adding the accelerator, so your performance will scale up linearly. So it's a very nice model for infrastructure in general. And so this kind of, I think, shows a little bit about what we think about the high-speed bandwidth here, right? Again, like there's multiple optimizations and multiple abstractions. The SSD doesn't need to be block storage. It could be key value. And we see that there is an opportunity to optimize the interconnect and then optimize the different analytics that can perform in the CPU cores, the memory, and the hardware accelerator. So that's really the argument here. And we think it's a good idea to use it when the PCI bandwidth becomes a bottleneck. If that's a bottleneck, go ahead and use a computational SSD. Anytime you have ingest requirements like data needs to be pre-processed or post-processed, this is a great place to do it. So that would be a second place you want to do it for analytics. The third approach I would say is something like video delivery. The video processing is not that well suited to a CPU ISA anyway. So if you're doing video delivery with a certain transcode or a scaling mechanism, then you really don't need a high-powered CPU at all in the system. You can use a very embedded CPU for control plane and then deliver video directly through and orchestrate it through the software, right? So that would be a great place to use computational storage. You can combine video processing with storage. And then I think the most important one to think about is taking pieces of software in your current environment, see what portions are data intensive, move them out into the ARM cores, either as a container or as a application, and then run those applications on computational storage. There are certainly areas where you don't need a computational storage. Again, like if you have a compute-heavy workload, I think machine learning inference usually falls into this category, where it's a large workload, but it's not very computational storage friendly because it's really memory bound. And again, there are other like if your data set itself is small, then you can fit it in the memory inside your DRAM, then go ahead and use in-memory compute models. They will be faster, right? So that's also another case where you could skip a computational storage. And then with NAND being highly parallel, you want to actually target workloads that are parallel. If your algorithm is fundamentally sequential, it's probably cheaper to just move the data and compute it. Okay? So that's kind of the high level. I think it's good to have a system level hat. Think about Amdahl's law and kind of balance compute and storage. And I think there are several applications that will fit into the computational SSD paradigm. I won't cover this in too much detail, but we have an open source runtime library. And this is basically software. There's a software shell that runs on top of our hardware. So we try to make our hardware invisible to you. That's the entire job of our software runtime. And then something like the key value video encoder and machine learning in this chart, right? They are more like your software APIs. You have built some hardware, and then how do you talk to the hardware? That would be through those software APIs that connect to standard frameworks. And then these frameworks would be essentially talking to applications. And there's a rich application ecosystem that we built for the compute kind of, when we built the AWS FPGA service model, we built a lot of compute partners, and many of those partners are now working more on the storage platforms. So again, this is a little more about some of the runtime optimizations. All of this slide here, the Xilinx runtime stack is all open sourced. So essentially, anyone can go change it to their needs and optimize it. We know that it's very hard for us to go optimize for everyone. So this is open sourced. I won't have too much time to cover that. This slide is basically talking about having one hardware SKU that's reprogrammable, and you can provide many services. You can provide many services as many different SKUs, or you can provide many services more real time. Some of this you see in the edge, where you want to spin up and down services very quickly. So you may want to provide a Netflix video service, and then spin that down and provide an online gaming service, right? So that kind of thing you could do over time. I actually wanted to cover this, so I'll skip the rest for now. But this is basically our partnership with Samsung. This is the smart SSD that now we have this as a prototype, which is a add-on card, PCI add-on card, that has a FPGA and the full SSD on it. And we have a few applications running on that. In second half of this year, we're going to have, Samsung is going to build a next generation smart SSD, which is a U.2 card. So essentially, each U.2 card will go into there could be 24 slots in a 2U server, for example. You could put 24 servers, totally distributed, totally scale-out model. And that's the production Samsung next-gen smart SSD. We do have a add-on card today for application partners to work on. So if you have interest, talk to me after, and would be really interested in going over that. This is essentially kind of the framework. This runs on the software stack that I showed earlier on and connects to the framework, so you would be able to connect to many different applications, right? And then a couple of examples here. One is MariaDB database, which showed a 2.8x improvement for the TPCH score. And then there's a financial analytics example here. I'll let you go over it offline. So to recap everything, I think major advantages in latency, major advantages in throughput, but I think the biggest advantage is going to be the lowering the cost of the infrastructure. We want to be able to reduce the number of servers by using computational storage. So I think that's the biggest advantage. And then we do have the Samsung Smart SSD for application development. So connect to me if you want to use that platform. And then finally, the SNIA Computational Storage Group for standardized computational storage. Join the group, and we'll look forward to working together with you. And yeah, I think this is going to be a big change, so let's create it together. Thank you.